So this is one of those videos where we want to go back and state more carefully and prove some of the things that we have been using on a regular basis. So what we would like to show here is the following, that if A is in Z, so the set of integer numbers, and N is in N, so this is a natural number, then there are unique M, comma R in Z with R being between 0 and N minus 1, such that A is the same thing as N times M plus R. So this is the good old division that we all learned in elementary school. In fact, this is the dividend. This is the divisor. Oops, I shouldn't forget the S. So this is the divisor. This is the result of the division, if you like. And this is the remainder, which in our theory, maybe it's the most important quantity. So what we would like to do is actually prove this statement that we can always find these numbers and that they're unique having this property, which is a very, very standard thing to do. So how is it done? So the classical way of doing this is to consider the set A minus N times T, such that T belongs to Z, and A minus NT is greater than or equal to 0. Okay, so we do this in order to show the existence, and then we will see that uniqueness is actually quite simple. So let's call this set A. And then we have two cases. First, we have the case that, so first of all, it would be nice to show that this set is non-empty. So A is non-empty. And the classical thing to do here is to just take a huge, it doesn't even have to be huge, number, which is negative, as RT. So if we take, for example, A minus N times, and now take minus the absolute value of A. I'm putting absolute value so as to make sure that this is positive. I'm sorry, this is large enough. And we can even put -1, and you will see why. So how much is this? This is the same thing as A plus an absolute value of A plus N. I just want to give myself some ridiculous amount of space here. And now, so this is a positive number, and this is greater than or equal to A. And certainly, if A happens to be negative, then n times absolute value of A plus A is going to be non-negative. Okay, so this is because the absolute value of A is greater than or equal to negative A, so you can see that A plus A is greater than or equal to 0, and certainly if you multiply by n, which is at least 1, you will still get a greater than or equal to 0 number. So this is greater than or equal to 0, and of course this is greater than 0, so the whole thing is greater than 0. So our set has elements, and it certainly has positive numbers. Okay, so this set is non-empty. Okay, again, we're making a big fuss about something simple, but we just want to give all details. Now, if 0 belongs to A, then A is written as NT for some T. And this is already what we need in our statement. Okay, so here we could take, this would be our M, and then 0, which we can think of here, becomes our R, so we're good here. So we can find numbers like this. If 0 does not belong to A, then A is a subset of n, of the natural numbers, and it's non-empty. This is where the fact that it contains positive numbers that we showed before kicks in. So by the well-ordering axiom, it has a least element. Okay, so by the well-ordering axiom, it has a least element. And let R be the least element. So in other words, we write R as A minus NT. And we claim that R has to be less than or equal to n minus 1. We claim that R has to be less than or equal to n minus 1. If not, then R is greater than or equal to n. And so we could write now R minus n. So we could subtract n from both sides, and we could write R minus n is equal to A minus n times t plus 1. Okay, and then all of a sudden, we have that R minus n is greater than or equal to 0. In fact, we suppose that 0 doesn't belong to A, so we could say that R minus n is greater than 0, right? And it's certainly less than R. And it bears the description that the elements of A have, and that's a contradiction to the fact that this was the least element. Okay, so if R hopes to be the least element, then it better be less than or equal to n minus 1. So this means that R has to be less than or equal to n minus 1. And of course, from the description in this case, at least we know that R is greater than 0. And we're done in this case too. So we're done in this case too. So existence has been established. So the numbers M, R do exist. Okay, now imagine that you can do this in two different ways. So you can take A and write it first as N times M1 plus R1. And then you can also write it as N times M2 plus R2. And here you do something pretty standard. You subtract the two things that are equal, and you get N times M1 minus M2 plus R1 minus R2 is equal to 0, which of course gives you N times M1 minus M2 is equal to R2 minus R1. And here we can make the concession that so first of all, look at R2 minus R1. If R2 minus R1 is 0, then that implies immediately that M1 is equal to M2. So, so they are the same, right? So now if R2 minus R1 is greater than 0, and I'm saying you can take it to be greater than 0 because if it goes less than 0, then you can just reverse the roles of M1 and M2 and of R1 and R2. So you can subtract those numbers in the opposite way and just make sure that it's greater than 0. Or if you like, you can multiply both sides by -1, anything that you like. But if R2 minus R1 is greater than 0, then certainly R2 minus R1 is less than N, right? And then this equality tells you that then N divides a number, a non-zero number, less than itself. Okay, that's impossible because all divisors of a non-zero number have to be less than or equal to the number. Okay, so that's impossible. So that shows you that there's no way in the world that R2 minus R1 can be greater than 0. So this fails, and this establishes uniqueness. So here, again, we gave all details and possibly to a nauseating degree. And it's conceivable that one could write a more concise proof for this. But we would like also to repeat something that we have in an earlier video, how that works for negative numbers. So let's say that we do division by 5, okay, just for the sake of the argument. Nobody would have any trouble saying what the number should be for 13. So for 13, our M should be 2. So that's our M, our result. And our remainder is 3. So this is the remainder R. Right. What becomes interesting is what if it's -13? And when we have -13, people tend to automatically think that you will take that the equality for 13 and just take its negative, and that will give you everything that you want. But then you have the absurd situation that the result is -2. That there's nothing wrong with that, but that the remainder is -3, and remainders have to be between 0 and 4 when you divide by 5. So the right thing to do here is to say that this is 5 times -3, which is -15 plus, and the remainder is 2. So here M, this is M, this is R. So one has to get used to how this division works for when the dividend is negative. And that's the one thing that seems a little strange in the beginning when one encounters Euclidean division. And that's all. Thanks for watching.